we have a rope and it's being wound around a drum, and the drum has a radius of 0.8725 feet. And we want to know how much rope will be wound around the drum if the drum is rotated through an angle of 39.72 degrees. So imagine that you have a giant spool of rope, okay? And what I always think of when I think of this problem is, have you guys ever used the ribbon that comes on a spool? And you get to the end and you see where the end is taped down to the spool, and then obviously they started rotating it and they like pulled all the ribbon up onto that spool. That's what I think of here. So imagine looking like straight down onto the spool. So if I draw it this way, here's my drum. It's acting like my spool, okay? And then we say the radius is what, 0.8725 feet? So this is 0.8725 feet. Now imagine that I tape or somehow I bind the rope on at this point. So, you know, I get the rope there, and then I start spinning this. Like if I spin it downwards, it's going to pull the rope up onto here. Or you could spin it that way and it would pull the rope down to here. But I could start spinning it and rotating it to start wrapping that. You know, we do our garden hose like that. Like we put it on a spool and we wind it up to keep it out of the way. Yeah. So that's what's going on here. And I rotate 39.72 degrees. I want to know how much rope is now attached to that drum. So I'm looking for the arc length. So that's the first thing you have to do, is you have to recognize this as an arc length problem. Now we know our formula for arc length is S equals R theta. And our radius is 0.8725 feet. But I don't know my angle because I have to list that in radians. So I'm going to come off to the side and I'm going to convert 39.72 degrees into radians. So we're going to multiply by pi divided by 180 degrees, cancel our degrees, and we'll clean that up and list our angle as an exact radian measure. So did you guys get 331 pi over 1500?
Yes.
Oh, that's gross. Okay. 331 pi over 1500 radians. And that's what we're going to use as our angle. So we'll substitute it in. All right, if I take the 0.8725, multiply by 331, divide by 1500, I get, ooh.
Really nasty.
I have no idea. Okay, let's try that again. So 331 times 0.8725 divided by 1500. Math inner. My calculator didn't like it. It did not even want to turn it to a decimal. How about yours?
Yeah.
Mine did not. It was like, I'm not doing it.
It won't
So
turn it to
let's go
a
ahead and put the pi in and see. It's just exceeded the capacity. Did you guys get 0.60485? Yeah. Okay. So 0.60485606696 feet. It's bad when a problem exceeds the capability of your calculator to do a fraction. That's when you worry. But we're going to round it to 4 significant digits. So how about 0.6049 feet? That's not very much road, right? Well, why didn't I just measure it with a tape measure?
Why are you winding a rubber on the drums now?
Well, haven't you ever gone to Home Depot and bought rope? You can buy them. They come off of drums. You know?
Oh.
Yeah. Or maybe, like, have you ever noticed when they dock a cruise ship and they reel them in? So maybe they have to reel at a certain angle to get it, you know, situated in there properly so that everything can be seated. So maybe that. But my question is, why didn't they just measure it with a tape measure? Anybody know? I couldn't get that precise with the tape measure. So if it was something really important, like, you know, I didn't want to tip over that cruise ship or what have you, then maybe I need to know a little more
I know
precisely.
they use it in
crabbing boats and shrimping boats because my uncle used to work on one.
They use it to like bring them in, or
Bring them in.
Yeah.
And get them out the way as far as they want them.
yeah. So they actually, this has a lot to do with like shipping and that sort of thing. Okay, so here's what we have. 2 gears are adjusted so that the smaller gear drives the larger one. That's typically how gears work. If the smaller gear rotates through an angle of 225 degrees, we want to figure out how many degrees the larger gear will rotate. Okay. So the gears are hooked together, and the gears have 2 different radii. The smaller gear has 2.5 centimeters, and the larger has 4.8 centimeters. And when we turn them, they'll also have different angles of rotation, which is interesting. The larger one will actually have a smaller angle than the smaller one. And that kind of makes sense if you think about when you put larger tires on a bicycle, you don't have to pedal as hard, right? To get it to go as far, because it covers more distance. No? Okay. Well, anyway, but what are they going to share? The way they're hooked together and they're turning, how far they turn, right? Well, that's, for a circle, how far you go around the outside is called the arc length. If you go all the way around one time, it's called the circumference. So that's how gears work. They have different radii, they have different angles, but they produce the exact same arc length or portion of the circumference. Make sense? Okay, so it gives me some information, and it tells me that the smaller gear. So the smaller gear has an arc length of r theta, where theta is 225. Well, I need to know what that is as a radian. Instead of doing 2 separate pieces, I'm just going to go ahead and I'm going to put r theta, and theta is 225 times pi over 180. Do you guys mind if I just do that in one big step like that? Is that okay? Okay. So that's going to produce the arc length, and I want you to stay exact. Give me that arc length. 2.5 times 225 times the conversion factor of pi over 180 to force it into radians. Do we need to pause, or does someone have it? I think we'll pause. So when I multiplied that out, I got 25 pi over 8, and that is centimeters. That is my arc length. Make sense? Okay. Now let's look at the larger gear. For the larger gear, I also have the equation S equals r theta, but it has a different radius. It has a radius of 4.8 centimeters. What's its arc length? That's its arc length, right? They share the arc length. So in this case, I'm solving for theta, not the arc length. So we have 25 pi over 8. So we substitute that in, and that will let us find theta. So we divide both sides by 4.8, and I want to know what 25 pi over 8, and I'm going to leave the pi. I'm going to hold the pi. So I'm just going to do 25 over 8 divided by 4.8. Did you guys get 125 pi over 192?
Yes.
Me too. 125 pi over 192. And I didn't type the pi in yet. Remember that pi is like the dessert course. You save it for the very, very, very end. And this is not my final answer yet. This is my angle in radians. I asked you to give me that angle in degrees. So now we can convert it all. Go the other way and multiply by 180 over pi, and that will give us our angle in degrees. And the pi's cancel. 125 times 180 divided by 192. I got an angle of like 117.1875. That's degrees, and I'm going to round it to 2 significant digits. Actually, I'm not. I'm gonna just overtake the problem. Round it to 3 for me. So 117 degrees. A lot of times I'll tell you to round the angles to something else.
So for this one, you want us to put it back into degrees?
Well, only because the problem asks you to.
Okay.
Now, when it comes out of the problem, it comes out
In radians.
in radians, yeah, because that's how that formula works.
So,
That formula goes in and comes out in radians,
but
and that's
if it
true all the
hadn't
time.
Asked how many degrees we would have.
If it hadn't asked how many, you could have left it right here at 125 pi over 192
Okay.
as radians.
Okay.
It's just that that doesn't mean anything to us, so usually we will ask you at the end, if we're looking for degrees, to go back there.
Well, the reason I ask is a lot of teachers are like, even if it doesn't say anything, keep it with whatever was given. So.
True, but I'll be pretty specific, and if you don't know, just ask.
Okay.
For our second application, we're going to look at the area of a sector. A sector of a circle is the portion of the interior of the circle that is intersected by a central angle. So it's a piece of the overall area. Now, if we're going to find area of a circle, the whole circle, it's real easy. We just multiply pi times the radius squared. It's a little harder if you're looking for area of a sector. So like we think of it as a little piece of pie. And out west, because it's so difficult, they don't have a lot of rain, they won't actually irrigate their entire rectangular fields. They will irrigate only a circular portion of them. So it's actually better sometimes if they don't plant the entire rectangle. They will irrigate so that their irrigation system can rotate around and around and around. So they actually need to know what area needs to be covered there and what angle of rotation to set up that irrigation system to do over a certain amount of time, depending on what types of crops are planted. So it actually does become an issue, believe it or not. If you've ever flown out west and landed somewhere, you come in and you can see those circular, they look like crop circles or something, but it's actually just the parts they've irrigated. Yeah. But out here, when you fly over like Mississippi in this area, we have so much water that it's always rectangular. You don't start to see the circular fields until you get out west, where irrigation is a major cost. Yeah. So we want to talk about that, and I'm going to give you a formula for it. Are you ready? And you need to memorize this formula. The formula to find the area of a sector of a circle is always equal to 1/2 r squared theta, as long as theta is in radians. So the area of a sector is 1/2 times the radius squared times the angle that you are intercepting, as long as it is in radians. So arc length and area of a sector both only work if the angles are in radians. It'll go in as a radian, it'll come out as a radian if you're asked to calculate the angle. So that's the formula we're going to use anytime we're being asked to find a portion of the area of a circle. Be careful though, your angle must be in radians. Anything to deal with circles needs to be in radians unless you're specifically told otherwise. So we have a center pivot irrigation system that provides water to a sector-shaped field with the measures shown in the figure to the right. We would like to find the area of the field. So I don't know if it's easy for you to see, so I'll redraw it for you. This angle is 15 degrees. This radius is 321 meters. And I want to know the area of that sector that my irrigation system is going to irrigate for me. So I'm going to have it. It's going to water, and it's going to go this way and this way. It's only going to water that one little piece. We're going to program it to do that so we don't waste water. Not everybody's like Mississippi. You have to be very careful with their water in other places. You're very fortunate here. So what formula do I use? A equals 1/2 r squared theta. All right, before I can substitute in anything, I need to make sure that my angle is in radians. So we're going to take the 15 degrees. We're going to convert it by multiplying by pi over 180. And that converts to, is it pi over 12? 15 divided by 180, math inner, guys. It's 1/12. So it's 1/12 pi, so pi over 12. That is the angle I'm actually going to use. So substitute into our formula, 1/2 r squared theta in radians. And we'll pause again so we can get a computation. Okay, so when I typed all of that in, I got 13,488 0.03536 square meters. It's area. So that meters is going to square off there. And then if I round it to 2 significant digits, that's approximately 13,000 square meters?
Yes.
Yes? All right. Any questions or you're good?
Good.
Okay, great.